Okay, so I've got Stokes' theorem written up here. We want to remember that C here is the boundary of S oriented positively with respect to S. And if I have a vector field and I'm calculating this integral, which if f is a force vector, this would be a work integral, I can, instead of doing that as a line integral, I can evaluate the integral of curl of f dotted with n over the surface S and do that as a surface integral. And at first glance, it might seem like we wouldn't want to do this, because in general, I think of double integrals as being more complicated than single integrals. And in order to even do this, we'd have to calculate the curl of f. That involves taking a cross product. So it seems like this is likely to be more work, and sometimes it is. But there are times when it's not. So here's an example where this is actually going to be a shortcut for us. So I'm going to have C be the boundary of the portion of the plane, x plus y plus z equals 1, that lies in the first octant. Okay. So we've seen stuff like that before. That's going to intersect the x-axis at 1, 0, 0. It's going to intersect the y-axis at 0, 1, 0, and the z-axis at 0, 0, 1. So we're talking about this triangular portion of that plane. Now, we're told we want it to be oriented counterclockwise if viewed from above. Now, that's important. In 2 space, clockwise and counterclockwise are well defined. In 3 space, clockwise and counterclockwise depend on your perspective. Okay, so right now, it probably looks to you like I'm drawing a circle in the air and like I'm going clockwise. Okay, I am not changing the way I'm rotating, but it probably now looks like it looked to me like I'm going counterclockwise. Okay. So whether something appears clockwise or counterclockwise depends on your perspective if you're in 3 space, and so that's why it had to be counterclockwise if viewed from above. So if I'm standing above this thing and looking down, it's going to look like it's going counterclockwise. So it would be like so. Okay. So if I wanted to evaluate that as a line integral, so I've got my vector field, here's my work integral. If I wanted to actually do that as a line integral, because that's a piecewise smooth curve, and it comes in 3 pieces, I would actually be doing 3 line integrals. Now I could do that, but I might notice that that curve is, well, I was told it's the boundary of this portion of the plane. So those 3 curves together are the boundary of 1 surface. So rather than doing 3 line integrals, I could do instead 1 surface integral. Okay. Now, if I'm going to do that, I'm going to need to calculate what the curl is, and I'm going to have to figure out what the orientation of the surface is. Okay. I know how the curve is oriented. I want that to be positively with respect to the portion of the plane. So I'm going to take my right hand, and I'm going to say, okay, if I were going around like so, that sort of gives me an upward direction for my thumb. Might actually be easier to say, here's the y plane. So if the x-axis is coming straight out here, I'm sort of happening on the x-axis, I'm heading back and to the right, okay? And then I'm going to curve to start coming up, okay. And it's a little hard to see that actually, but that is giving me sort of an upward orientation for things. Might actually be almost easier to imagine a little bear walking around the outside here, and if we're on the top of this portion of the plane, the surface is going to be to the left. Okay, so this is going to be oriented upward. If I call this region here, if I call that surface S, it would be oriented upward in order to have this be the positive orientation with respect to the surface. Okay, so let's calculate the curl of F. So remember, curl of F is del crossed with F. So that's going to be the symbolic determinant, I, J, K. The del operator has as its components the three partial derivative operators. And then I'm going to put the components of my vector field. So x squared, xy, yz. Okay. What that's going to give me, I'm going to write it over here because I've got some more space. In the I component, I'm getting the partial of this with respect to y. That's going to give me just z. Minus the partial with respect to z of xy. That's 0 because there aren't any z's in there. Okay. For the second component, remember to go this way because it's negative. Partial with respect to z of x squared. Well, that's 0 because there aren't any z's. Partial with respect to x of yz. That's also 0 because there weren't any x's there. For the k's, I'm getting the partial with respect to xy. The partial with respect to x of xy. That's going to be y. Minus the partial with respect to y of x squared. That's 0 because there aren't any y's there. Okay. So there's the curl of f. Okay. And so now, let me just write that down up here. Curl of f is z0y. And my surface was part of this plane, x plus y plus z equals 1. So I can easily solve that for z, and then I'll have z as a function of x and y. I'm kind of liking that. So I'll say z is 1 minus x minus y. Okay. And so now I can essentially use x and y as my two parameters. So I'm going to say this is the double integral over s of curl of f dotted with n ds. That's going to become the double integral over d. That would be the region in the xy plane. That's the domain that maps to this. So if I projected this plane onto the xy plane, I'm getting that triangular region in the xy plane. In fact, I know the x-intercept was at 1 and the y-intercept was at 1. So it's that triangle with, in the xy plane, this would be 0, 1, and 1, 0. Okay, now I'm going to write curl of f, but I'm going to replace any z's with 1 minus x minus y. So we're going to have 1 minus x minus y, comma 0, comma y, dotted with, and I'm going to now dot with the non-normalized normal vector because that will absorb the scaling factor that allows me to switch from ds to dA. Now, we said we wanted this oriented upward, so I know I want the z component to be positive. That means that what goes here is the opposite of the partial of z with respect to x and the opposite of the partial of z with respect to y. Well, let's see, partial of z with respect to x would be negative 1. The opposite of that will be positive 1. Partial of z with respect to y is negative 1. The opposite of that is positive 1. Now, I can see from this plane, I can just pick out 1, 1, 1, this is going to be normal. I needed to actually get it from here, however, because there are infinitely many vectors that are normal to the plane. 2, 2, 2, 3, 3, 3, 4, 4, 4. Those are all going to be normal to the plane. I need this one. This is the one whose magnitude is the scaling factor that allows me to switch from ds to dA. So remember, when you're finding this non-normalized normal vector, you care about both its direction and its magnitude. Okay, excellent. So let's do that dot product. This is going to be the double integral over d of 1 minus x minus y plus 0 plus y dA. Oh, that's lovely. That's the double integral over d of 1 minus x dA. I'm liking it. Okay. So let's write that now as an iterated integral. Notice this line would just be y equals 1 minus x. So if I slice things this way, I can say, well, my slices start at 0 and go to 1. Those are going to be my x limits of integration. But along each slice, my y value is going from 0 to the y value on that line, so from 0 to 1 minus x. I'm integrating 1 minus x, and that would be dy dx. So we will have the integral from 0 to 1. Taking antiderivatives with respect to y, I'm going to get y minus xy, and that's evaluated between 1 minus x and 0. And then we'll still have to integrate that with respect to x. Okay, so that's the integral from 0 to 1 of 1 minus x times 1 minus x. That's what I get if I plug in 1 minus x. When I plug in 0, everything just goes to 0, dx. So that's the integral from 0 to 1 of 1 minus x plus x squared, just distributing that negative sign. And then I can consolidate some like terms, so it's the integral from 0 to 1 minus 2x plus x squared dx. So that's x minus x squared plus x cubed over 3, all evaluated between 1 and 0. When I plug in 1, I'm going to get 1 minus 1 plus a third. And when I plug in 0, I'm going to get 0. So all of that, and we get 1/3. Okay. Now, that took a while. Okay? These integrals do tend to take a while. Okay? But I still think it was probably faster than parameterizing 3 separate line segments and doing 3 separate line integrals. Although we certainly could have done things that way, and we would also get, if we do that, 1/3.